As the last topic in this extension material, I thought it'd be worthwhile to talk about the energetics associated with nuclear chemistry, because this is when your average member of the public thinks about nuclear. This is what they think about: the nuclear bomb, a really high energy bomb. Nuclear power plants generating energy via nuclear chemistry. Now, in order to do that, we'll have to go back and do a bit of physics, and I hate physics, so I'm just going to do this very, very quickly. But all the way through our careers, even in chemistry, we've abided by the law of conservation of mass. That's what we use when we balance chemical equations, and the law of conservation of energy. That's what we use in calorimetry and so forth. And we think of mass and energy as being two separate things. However, Einstein came along and said, no, actually, mass can change into energy and energy can change into mass, so they're not separate. So what we actually need to think about is the law of conservation of mass and energy. You got a total amount of whatever. It can be mass and energy. A little bit of mass can change into energy, and vice versa. And the relationship between them is probably the most famous equation in the world. You see it in cartoons and comics when you're 2 or 3 years old. You have no clue what it means, but it's one of those things that, oh, E equals mc squared. I'm so intelligent. Well, what it is it's just demonstrating the relationship between energy E and mass m. Now let's see why we have waited this long in our chemistry deliberations, where we've talked all kinds of things about mass and energy. Let's see why we haven't bothered with this so far. Typical chemical reaction, change of 200 kilojoules per mole. Okay, well, 200 kilojoules is 200,000 joules, and of course a joule is a kilogram meter per second squared. So that's our energy, 200,000 kilograms meters per second squared. That seems really big, doesn't it? Let's pop it into the equation. 200,000 kilograms per meter squared per second squared is times the mass in kilograms times 3 times 10 to the 8 meters per second squared. Okay. Well, let's rearrange that to find out what the mass change is associated with 200 kilogram meter squared per second squared, 200 joules. The answer is that the mass is 2.22 times 10 to the minus 9 grams. So in other words, when we have a chemical reaction associated with 200 kilojoules, the mass change is 0.00000000222 grams. Who really cares? And the answer is you don't. Okay, so chemical reactions, even though there is a mass change associated with the energy change of the reaction, it's absolutely negligible. However, let's look at our fission reaction that I exemplified in the previous movies. Okay, we say the mass of 235 uranium is 235. Actually, it is 235.0439. Well, it's close enough, right? And it always has been close enough, except for now. Mass of a neutron is 1, right? No, actually, it's 1.0087. Well, what's 0.0087 between friends? Absolutely nothing until now. Mass of 138 xenon, 137.908, 95 strontium is 94.913, and there's those neutrons again, 3 of them at 1.0087. Now let's add up the mass on each side. The total mass at the start, 236.0526. Total mass at the end, 235.8471. Well, it's about 236. It's about 236. What's the big deal? Well, the big deal is that if we think about 1 mole of uranium, well, then we've gone from a total mass when it reacts with a neutron of 236.0526 to 235.8471. In other words, every time a mole of uranium undergoes this fission, there is a mass loss of 0.2055 grams per mole. 0.2055 grams. That's actually a significant mass deficit. Where does that mass go? Well, it gets turned into energy according to E equals mc squared. Okay. 0.002055 kilograms per mole. Okay, pop that in. the energy in joules associated with this much mass, 0.0002055 kilograms, who gives a crap, but multiply it by 3 times 10 to the 8 squared, and what you find is that that energy change is 1.85 times 10 to the 13 joules. Okay, chemical reaction, 200 kilojoules, nuclear reaction, 1.85 times 10 to the 10 kilojoules. In other words, 18.5 billion kilojoules. Chemical reaction, hundreds. Nuclear reaction, billions of kilojoules. The energies associated with nuclear processes are massive compared to the energy associated with chemical reactions. Now, as a last little concept on this, we can get a feel for why our nuclear process is so energetic by just thinking about what goes to make up a nucleus. A proton weighs 1, right? Neutron weighs 1. And a mass of a hydrogen 1 atom, which has a proton and an electron, is of course 1, because hey, an electron weighs nothing. And that's been fine throughout our entire lives. But the mass of a proton is not exactly 1. It is 1.007276. We've already seen a neutron was 1.008665. And when we take a proton and an electron to give us that hydrogen atom, 1.007825. So I'm just using this to make our subsequent calculations easier. This is a proton plus an electron. Now let's think of an atom of carbon-12, which until very recently was used to define a mole, because we said 1 mole of carbon-12 weighs exactly 12 grams. Okay, now that atom of carbon-12 has 6 protons, 6 electrons, and 6 neutrons. Let's consider the 6 protons and 6 electrons to be the equivalent of 6 H1 atoms. Okay, so the atom itself weighs 12.0000000. We have, as part of that, was made up 6 protons and electrons and 6 neutrons. Let's look at the mass. 12.00000 defined for carbon-12. 6 times 1.07825, 6 times 1.08665. So just in the atom itself, we have a mass difference of 0.09894 AMUs per atom, or 0.09894 kilograms per mole. So the particles themselves, 12.09894, coming together to make an atom of 12. So in other words, there has been some mass lost as we go from the particles to the atom. And that's energy that's contained in the nucleus, so-called binding energy. So again, see how large that binding energy is. Well, the mass defect and the mass deficit, the difference in mass here, 0.00009894 kilograms per mole. Pop that into our equation, and we find that the binding energy for 1 mole of carbon-12, that's the energy in the nucleus waiting to be released, 8.9 billion kilojoules. Okay, nuclear energy, the energy associated with the nucleus, is so enormous, so massive, right? Because the actual mass changes associated with even making a nucleus from its particles, let alone doing reactions with it, the mass changes are so significant when you turn them into energy. Now, as one last little note, just as a nod to physicists, an awful lot of times you don't think about this in such huge masses. You do it in terms of electron volts. Now, 1 AMU, right, so that's the atomic mass unit, is equal to 931.5 mega electron volts. So here, the actual energy associated with a carbon-12 atom, or with a carbon-12 nucleus, 92.16 mega electron volts per atom. And then we divide it by the number of nucleons, right? A nucleon is a nuclear particle, so that's a proton or a neutron. And for carbon-12, we get the number 7.6 times MeV per nucleon. The higher that number is, the more stable the particular isotope. The smaller it is, the more unstable, the more likely it is to be radioactive. Could do an entirely new movie on that process, but right now I just wanted to give you a little taster of some nuclear reactions and the energy associated with nuclear processes. And as you've seen it, I also wanted you to just see the other ways this could be expressed in MeV, mega electron volts, per atom or per nucleon. Hope you enjoyed it.